So this is Basic Physics 1. We're going to have just a general introduction to physics in this chapter. We're going to talk about what it is and some of the basic concepts. Some of these things will apply to all areas of science. So in physics, we have, and really in all areas of science, models, laws, and theories, maybe. I'm speaking a little loosely. So models, you've seen a skeleton, a plastic skeleton that's a model, a skeletal model of a human, or a large model of a cell. You know, this is maybe a cell in biology or something. These are physical models, right, where you have something that you can pick up that represents something else. And so I would call this a physical model. But there's also things like conceptual models. And this is just a simplified representation of reality. We'll use conceptual models. We'll use both, but we use conceptual models a lot. So, for example, when we talk about projectile motion or throwing a ball or something like that, we'll neglect the air. So we'll create a model where the Earth is flat. I'm throwing a ball from here to there. I don't have to worry about the curvature of the Earth. There's no air resistance. I don't include things like the variation of gravity with height away from the Earth's surface. Gravity gets weaker. I'll neglect that. So we create conceptual models that are simplified representations of reality that retain most of the science but simplify the representation so that you can solve the problems with algebra, say, or something like that, and still get a reasonable answer. And so that's models. And so I'll just say a few things about laws and theories, right? Laws in science are hypotheses that stood the test of time. So a hypothesis in science is any falsifiable statement. So I might say objects attract each other with a gravitational force that depends inversely on the square of the distance between them. That would be a hypothesis. That was Newton's law of gravitation. It's just a hypothesis at one point, and then over time people try to disprove it, or people test it in various ways. They look at what happens when you drop a rock. They look at the motion of the moon around the Earth, or the sun, or the Earth around the sun, or what comets do. Eventually people come to the conclusion that, yep, that one's right, and so we're just going to start calling it the law of gravitation rather than a hypothesis. And that's kind of how things become laws. Often a law can be represented as is Newton's law of gravitation with a single equation, but not always. Usually laws are directed at one specific area of science. Sometimes a less specific law or a less general law. So for example, Newton's law of gravity works for almost anything, except in very, very few cases that we encounter. Well, in cases near stars or near extreme gravity or at high velocities, things like that, there corrections have to be made to it. But for most of our experience here on Earth, Newton's law of gravitation works great. But there are other laws like Bernoulli's principle, which talks about how air flows over wings. that only works in a small select set of cases, even on Earth. Even though it's large enough for it to be important, it's not nearly as universal as Newton's law of gravity, and so we call that a principle. It doesn't matter the distinction between those two, really. But anyway, we collect laws, and by the way, laws are not provable. Nobody has proved Newton's laws of motion. All we do is we look at them over time and say, yeah, this seems to be the way the universe works. And that's kind of true in all areas of science. And finally, theories. That it often gets people confused because in the normal language, in the lay people language, in the non-scientific language, a theory is what a scientist would call a hypothesis. My theory is that my car won't start because the battery's dead, right? That's not what a scientist calls a theory. A scientist calls a theory a collection of maybe of laws or concepts that are all related to one area. So the kinetic theory of matter is a collection of laws and statements about how small particles interact in gases and liquids and things like that. Atoms and molecules interact in gases and liquids. The theory of the atom, the quantum theory, is a collection of a set of really postulates about how the atomic world works. And there's no concern that these are in error any more than these laws are. They're just collections of statements that are focused on a specific area of science. So the theory of evolution in science, at least, is not considered a hypothesis anymore. For example, neither is Newton's theory of motion or the kinetic theory of matter or the quantum theory. Any of those are all considered by scientists as well accepted and established areas of science. And so those are a few just basic statements about laws, models, and theories. You've probably all seen that before if you're in a physics class at this point. I'm going to talk about some more things you've seen before. We talk a lot in this class about physical quantities. Which I'll generate as I'll call PQs, right? Physical quantities are measurable properties of matter. And this is a fancy way of saying it's things we can measure. So length is a physical quantity. Time is a physical quantity. Mass is a physical quantity. Weight is a physical quantity. Force, weight is a type of force. That's a physical quantity. Momentum, energy, area, volume. You can sort of see. I'll write some of these down. Distance, speed, velocity, acceleration, mass, weight, force, momentum, energy. You can think of them on your own. Anything you can put a number to. Temperature, pressure, area, volume. As you can see, the list goes on and on. Often these are, here's another one, time. I left that one out. That's kind of one that we need to talk about, so I'll put that back in. We could talk about charge. I'm not putting these in any particular order, or current, maybe voltage. Over the course of the 2-semester Physics 1 and 2 class, you'll see all of these. Charge and voltage and things like that will come in the second semester, but certainly mass and distance and time and weight and force and momentum and energy and temperature and pressure, I think those will all come we'll talk about all those this semester, and you've probably seen them all. before. So there are certain physical quantities that are what we call fundamental physical quantities. And those are the physical quantities that when you buy a universe, you get the physical quantity for free, kind of. And another way of saying that is they're all the other physical quantities are made up of those. And so I'm going to give you some examples. So here's one. Distance is a fundamental physical quantity. Time is a fundamental quantity. Mass is a fundamental physical quantity. Charge is a fundamental physical quantity. Temperature is a fundamental physical quantity. Another one is amount, which we haven't really talked about. And the final one is we can call it brightness. Brightness, if you can read that. It doesn't really matter. And so, for example, speed is distance over time. Right? Velocity is also distance over time, but velocity is different from speed because velocity includes direction. But its units are distance over time. Acceleration is velocity over time. And so it's distance over time, and so it's just these two again. Current is charge over time. Force is mass times acceleration, right? Which is again distance over time squared. And so you can make all of these other ones that aren't checked. You can make in terms of pressure is force over area. As I said, force is mass times acceleration. So you can do pressure. Area is just distance squared. Volume is just distance cubed. So these guys, I'll just sort of list them on the next slide. These are called fundamental physical quantities. Sometimes they're called dimensions, different from the three dimensions we live in, right? But they're often called dimensions. So these are the fundamental physical quantities: length, time, mass, charge, amount, temperature, and brightness. And you get these, if you buy a universe, you get these for free. These are the ones we'll use for the most part this semester. And so, if I call this one L and this T and this M, then I can say, velocity has dimensions of length over time. Acceleration has dimensions of length over time squared, right? Because it's velocity over time, which is length over time, or just length over time squared. Area. Let me try again on that one. Area has units of length squared. I already said force is mass times length over time squared. And so often we would say force has dimensions of mass times length over time squared. And keep in mind that I haven't said any units here, right? I didn't say seconds for time or hours. I didn't say meters or inches. I just said the generic dimension. The dimension is length, the dimension is time, the dimension is mass, right? The fundamental physical quantities, I can call them dimensions. Right. When I write an equation, if I have like velocity is equal to the initial velocity or the initial velocity plus the acceleration times the time, or something like that. Anytime I have a physics equation, the dimensions of each term, that is each thing that's separated by a plus or a minus sign, all of these guys have to have the same dimensions. Because I have to add apples to apples, I can't add apples to oranges. You can't say my speed was 10 feet plus 30 seconds. That doesn't make any sense. And so anytime I have an equation, each term in the equation has to have the same dimensions. And you'll notice if I just look at the dimensions of this equation, this is length over time, equals, again, length over time. I'm not asking you to know what this equation is. I'm just saying, look, that's velocity, that's initial velocity. We'll get to this some later time, right? Plus acceleration times time. This is an equation we'll use later on, right? And so if I look at the dimensions of these things, I already said acceleration is length over time squared, and now I'm multiplying that by time, and that gives each thing in units of length over time. And so all of my equations, if you understand the dimensions of your equations, you can often answer questions without even understanding the details of the problem, because you can look at an equation and say, oh, if I need a velocity, I have to multiply an acceleration by a time for the dimensions to work out. And so knowing the dimensions of the physical quantities you're interested in is really useful for being able to problem solve. So those are dimensions. I can give you another example of that. Suppose, for example, I said, look, the velocity is equal to p times t plus q times time squared. Right? So I'm saying this is a velocity and t is a time. And I'm going to ask, what are the dimensions of p and q? Right? Well, if I look at my left-hand side, my dimensions for my velocity is length over time. And so that means the dimensions of this quantity has to be length over time, and the same thing for this one. And so what I'm saying is if I multiply p by t and q by t squared, each of these has to come out to be length over time. And so p has to be in units of length over time squared, so that when I multiply by time, I get length over time. And q has to have units of length over time cubed, so when I multiply it by time squared, I get length over time again. So often you can tell something about a problem just by looking at the dimensions. For example, in this problem, I can tell that p is an acceleration, because as we said on the last sheet, acceleration has dimensions of length over time squared. And since p comes out as length over time squared, p has to be an acceleration. Okay, that's a little bit about dimensions. So, if the dimensions of force are mass times length over time squared, right? And the dimensions of velocity are length over time. If power is equal to force times velocity, so if power is force times velocity, what are the dimensions of power? And if power is also energy over time, what are the dimensions of energy? Right? And so let me give you one more. I can just say distance is equal to let me do it this way. X is equal to A plus B times T plus 1/2 C times T squared. If T is time, what are A, B, and C, where x is distance. So if x is distance and t is time, what are the dimensions of A, B, and C? So their dimensions, and then tell me what physical quantities they are. Are they mass? Are they acceleration? Are they force? You should be able to tell me what they are. And so these are a few questions that you should be able to answer.